It's now time to talk about our friend, the normal model. What I want you to understand is that in real life, we collect raw data, and that raw data can be graphed by using methods or graphs like stem and leaves, box plots, or histograms. This green histogram is representing whatever we've collected, but it's raw data. Do you see how it's not perfect? However, we superimpose on it this black curve, which is called the normal model. This normal model has certain proportions that are always true. And with that said, I want you to notice that the normal model doesn't fit our data perfectly. See gaps like this yellow here, where it doesn't fit? See, sometimes the data goes above the model. So what I want you to understand is that the normal model is theoretical perfection. When we talk about that, we're going to specifically refer to its mean as mu, which is a Greek letter, and its standard deviation as sigma, another Greek letter. And the reason why we usually use Greek letters when we have a model like this is that first, they're representing theoretical perfection, and second, usually only the gods know the true mean and standard deviation. For instance, if I said to you, what is the height of all boys in this country that are 17 years old? It exists, but we really can't find it. So because we don't know it and only the gods know it, we would use mu. When we have the histogram, which is in green, we have raw data. So we can find the mean, which we call x bar, and we can find the standard deviation, which we call s. So whenever we're dealing with the normal model, however, we're going to use mu and sigma, again, because they're theoretical perfection. So for a moment, I'm going to go look at an applet with you to kind of give you a better picture of the normal model. And here we go. I can shift the mean and the standard deviation on this. Where this red line falls is the mean, and you can see it cuts the normal model exactly in half. And the blue line is representing the concept of a standard deviation. So when I have this set right now, this distance from that center to the curve is equal to 1.428 standard deviations. Now we haven't technically defined that, it's going to come in a minute, but I want you to watch as I make that standard deviation smaller. 1.3, 1.2, 1.1. Smaller and smaller. Do you see how that distance from the center to the curve is getting smaller? There are more points closer to the mean. When I make the standard deviation bigger, focus on that blue line, you could see it's becoming short and fat. The proportions that exist in a normal model stay the same, except kind of the shape, whether it's close in and really condensed or more spread out, is what changes. Now, I can also shift the mean. This is basically a translation. It's not changing how fat or thin the normal model is. It's just shifting it. In general, when the mean is 0 and the standard deviation is 1, we consider this to be a standard normal model. So let's go now and look at a normal model. So going back into our presentation here, this is what we typically think of as the normal model. Remember, it's superimposed on real data. So the center, or what we call the mean, we're going to designate with the Greek letter mu. And then we move out in standard deviations. If we move one standard deviation to the right and one standard deviation to the left, we expect that we see about 68% of the population. Now, if I go further, and from the mean I go 2 standard deviations, 1 to the right, or 2 to the right, and 2 to the left, we expect to see 95% of our population. And if I go out even further, 3 standard deviations from the center to the right and to the left, we expect to see 99.7% of our population. So generally, if our data falls that most of it, or 68%, is within 1 standard deviation of the mean, 95 within 2, and 99.7 within 3, we consider that we can use a normal model. Sometimes it's not that close, but if it's at all close, we try to superimpose this normal model. Again, we're only getting estimates. With that said, this 68, 95, 99.7 rule is sometimes called the empirical rule. Some things you want to note is that what we're basically saying is almost everyone is going to fall within 3 standard deviations of the mean if you're using a normal model. And the other thing I want you to note is that sorry, I think there was just a little glitch there because I lost my place and I turned it off. So I had commented that most people are going to be, or most items, within 3 standard deviations of the mean if you're using the normal model. But I also want to stress to you that the normal model doesn't end. It's asymptotic to the x-axis. There are always going to be instances where people are way over 3 standard deviations above the mean. For example, you have really, really incredibly tall people that are more than 3 standard deviations above the mean. So even though heights typically of, say, men can be modeled with the normal model, we can't say that everyone will be within 3 standard deviations of the mean. Okay, so now we are ready to show you how to calculate standard deviation. So I have these heights here and all these different people. And you can see 54, 77, 67, 68, 46, 64, 62, 56, and 38. I'm going to input these in a list in my calculator. So what I suggest that you do at this point is stop the video and input these in a list in your calculator and call the list heights. Okay, after you've done that, what I want to talk about is the idea that standard deviation is technically the average difference, sorry about that, from the mean. So typically, if I want to find standard deviation, what I want to do is find how everything differs from the mean. So think average difference from the mean. Now I'm going to show you how to do this by quote hand, and then I'm going to show you how to do it quickly on the calculator. And you're never going to have to do it out by hand, but I want you to understand the formula. So in column A, you see all the heights. It turns out the mean of these heights is 59.11. So what I did in column B is I took every height and I subtracted 59.11. Now, remember how I said it's the average difference from the mean? But because of some of these are negative and some are positive, if I try to average them right now, they're going to cancel each other out. So what we do so that they're not negative is we square them. So if you look at column C, we've taken all the differences and squared them. Now we're ready to average them. So to average them, you add them up and you divide by n. So if you look here at my screen, you can see it's took the sum of square and divided by n because there were n scores. This right now is called variance. Variance is standard deviation squared. The units are wrong because we squared everything. So to turn it into standard deviation, I take its square root. So now let's look at our calculator and see how you would really do it. So with that said, you have your heights in a column, and that's all you need is to name the column. And I'm going to go to a calculator page, and I'm going to go, and I want you to write these steps down, menu, statistics, because you're now in the statistics part of class, to 1, stat calculation. And what you're going to do is pick one variable, statistics. You have one list. And what you're going to do is you are going to say what the name of the list is. Our name of our list is heights. You're not going to worry about frequency or anything like that. You're just going to hit OK. Now I want you to look here. And in fact, I am going to cut and paste this into your document because of this gives you so much information here. So here we go. Let's just go right here. Oh, sorry. Let's add a page. And let's make this smaller. Do you see I told you the mean before was 59.11? There's your X bar. Now, there's two standard deviations. The one that we just got was about 11.28. That's sigma. And this is for a population. There's another one which we use, which is S of X. Remember, S is when we don't know the true population. This is 11.97. This is usually from a sample, particularly for the old regions that you're going to take at the end of June. Sigma is for the population standard deviation, and S is for sample. So think S sample. Now, the difference is basically in formula, very minorly, in how your calculator calculates it. In the population, you're assuming you know the true mean. So you're taking each score, you're subtracting the mean, you square it. The sigma over here means add them all up and divide by n. Now, it would be variance until you square root it. But what happens is if you're dealing with the sample and you don't know the true mean, you're not subtracting the true mean, you're subtracting your sample mean. And what happens is your data is more likely to be closer to its own mean, not the mean of the whole population, so it's artificially inflated. So what we do is instead of dividing the sum by n, we divide it by n minus 1 to make it a little bit bigger, right? When you divide by something smaller, you make it bigger. So it's a little trick. So the sample standard deviation, instead of dividing by 1, 2, 3, 4, 5, 6, 7, 8, 9, you only divide by 8. Again, your calculator is going to do this all for you. You're just going to have to, on your own, kind of decide, am I using a sample or am I using, sorry, I was just checking my time there. Eek. Sorry. And I'm doing it again, trying to see if I'm going over or not. But you're going to have to decide, is it a population or a sample standard deviation? One last thing I want to show you, and hopefully there's time, is what if I had frequencies? So let's go list, and I'm going to go here, test, and I'm going to say frequency. So I'm going to say 100. There were 3 of them. 56, there was 1 of them. And I'm going to say 78, there was 3 of them. Now, I don't have to go to a calculator page. I can do the one variable stats right on the spreadsheet. Menu, stat, calculation, one variable stats. It's still one list because we really only have tests. We just have a second column telling us how many. The list is called test, and then we have a column called frequency, and now we hit OK. This is now the mean for all of the tests, and I want you to realize that there are not 3 tests, but 3, 4, 7 tests. This is the sample standard deviation in blue, and this is the population standard deviation. Okay, work on filling out the sheet that I've given you, and we will talk tomorrow.